the sun is in the state of so-called hydrostatic equilibrium. That is, it is stable. Basically, there is a tremendous weight produced by the top layers of the sun that is trying to crush the star. But what happens is that as you go deeper and deeper, the gas pressure increases, and it is this gas pressure that actually balances the downward push by the force of gravity. Okay, so basically, as one goes deeper and deeper into the sun, the weight of the top layers increases, but at the same time, the gas pressure, as you go deeper and deeper, gas pressure and temperature go up, so that basically the downward push by the gravity is balanced by the outward pressure exerted by gas. So let me make a cross-section of the sun. And here is the fusion core. Its radius is about 30% of the sun's radius. Now, that energy that is produced in the fusion core eventually makes its way out to the surface. And there are two mechanisms that are responsible for the energy transport. The first region, from about 30% of the sun's radius up to about 71% of the sun's radius, is so-called radiative or radiation zone. There, the photons, you have to realize that because of the high temperature inside the sun, all the atoms are not in neutral state. They've been ionized. The electrons have been stripped away from hydrogen nuclei. So you have a dense soup of charged particles, either protons or nuclei of helium, because 1/4 of the sun's mass is helium. There are also electrons. And photons interact very strongly with charged particles. So here, in this region here, what they do, they are constantly being scattered randomly in all possible directions. They execute what we call in physics random walk. So during radiative zone, the photons are making this random walk like a drunken sailor. And each link is maybe 1 centimeter long. And it takes a photon, on average, 1 million years after it has been produced in the fusion core to make it to the surface. And in the last region, from about 71% of sun's radius to sun's radius, the mechanism of energy transport is different. A so-called convection takes place. So we call this convection zone. So what happens there, it turns out that hot material in the interior, because it's hot, it has lower density, it's light, and the buoyant forces push it to the surface. Then it gives up the energy at the surface, cools off, becomes more dense, and as higher density material, it sinks back in. It's heated up again, and the whole process continues. So we have these so-called convective currents that take the energy from the edge of radiation zone and take it to the surface. This convection mechanism is basically what you rely on when you are warming water to make some pasta on the stove, right? It's precisely the same thing, no different, right? What is happening when you put the pot of water on the burner next to it, then because the pots are usually made out of metal because they conduct heat very easily, what happens is that the water layer next to the bottom is heated up, it becomes less dense, and the buoyancy forces it to rise to the top. It, of course, gives out some energy. The surface cools down, becomes higher density, sinks back in. So here, again, you have these convective currents. And if you look at the surface of the sun, you can see that it looks granulated, and that granulation is a direct consequence of convection. What I mean by granulated, it looks just like if you are cooking porridge in a pot, right? There are these little blobs that appear, and it turns out that the granulation of the sun's surface is direct consequence of convection currents near the surface.